Okay, so welcome back. So let's continue with our project. So last time we were talking about the hardwares or board, but the problem is actually there is one piece of hardware we didn't talk about, that is here. So because this one, if you remember, this is a to digital or digital to analog converter, and so basically it's responsible for communicate with the computer. So, but itself, this chip itself doesn't do that. So you need some kind of a interface to do it. So there is really two choices you can do. So the first one is using this guy. So this is from the National Instrument. It's called USB 6501. So this is called digital I/O 24 lines digital I/O interface. So this is really a cheap one. So have a USB socket over here, and there is 24 pins on the side, so you can have 24 pins to actually output the digitals into the signals as we see over here, right? So this is like 12 bits of the information needs to come in, and I could use this guy to communicate with that. Okay, as you can see, this one is it's pretty simple one because it doesn't do any computings. Or we have another choices. Okay, so it's this guy. Okay, because you can compare the size. Okay, so this one is much smaller. Okay, this is called Arduino board. You can see over here. So this also have it's something like this, and so it's much smaller size computer here. It have a USB port over here, and on the side there have several pins on it. Okay, so if you see here, so actually like maybe this here, this one is actually to see better. So over here, so this is this guy. Okay, so this is guy, and USB 6501. So we have many pins on that, as actually 24 pins. So you can buy that, and relatively cheap. So like if you go to Taobao, this is a very cheap one, $200, 200 or 300. If you got, I don't know whether this is a really legit models, or this is a knockoff models something, because usually this costs something like $800 or something. I mean, it's like Hong Kong dollars, so like 100 US dollars around. Okay, so for this guys, okay, it's more advanced. So this is a Arduino Nano. So it's open source one, because here this USB port interface that do, as I said, do nothing but communicate with the computer, right? So, but this guy is much more advanced, so it do much more than just interface with computer. So, because basically have a little chip, as you can see over here. So this chip is actually a small computer. So this is called a microcontroller. So this can run without computer itself. So you can input the program in it and doing a lot of things on that. So it have a much more capabilities of doing, because over here you can see there is a many digital output. Actually, they have a somewhere like a 22, something like a 22 or something, 26 digital output, and have a digital input as well, and they have a computing powers, and you can connect it with a lot of sensors, things like that. So this is like you can, if you're using this, you can do robotics or a lot of things. So as I said, so this guy, okay, Arduinos, they have a different format. So this is called Nano, so this is actually smallest factor, and you have Arduino Unos, so that is a little bit larger. Obviously, it's going to be a more expensive, right? So, but anyway, so this one is very cheap. So as you can see, this guy, 25 Hong Kong dollars or something, or like 30 Hong Kong dollars or something, and the Arduino Unos, that's a little bit larger ones, probably 100, so or $80, something like that. But this one is the two choices. So we're going to see, okay, which one we're going to choose, because the thing is. From programming point of view, maybe because this is coming from a national instrument, so they can communicate with the Labviews a little bit more conveniently. This guy's, okay, Arduinos, it's still very simple. Okay, it's still very simple, but it actually do much more. So the main difference is obviously the size. Okay, so this size is so large and this size is so small. Because if I want to put everything, okay, into the small box, so for this guy, it's probably not possible because I have the PCB board. I make it small, but like I have a case and I need to put this guy in. It's going to be difficult. If I put this guy in, it's going to be much easier. All right, so we're going to choose this one, so Arduino Unos, okay, Arduino Nanos as our interface to communicate with the computer. Okay, so this guy's put it aside. Okay, so in order to communicate your Arduinos, this board, to the computers, so you need several things. So firstly is a USB cable. So like this is a little bit different to USB cable. So this is a little bit old style USB cable. So this is called a USB micro. And the Arduino is taking this Arduino Nanos is taking that. So you just like plug it in. And the next thing you needs to install a few softwares to allow the Labviews to communicate with this. Several things. The first thing is is called Arduino IDE. So firstly, you might want to make sure when you actually plug in your board into the computers, so the computer can recognize it correctly. Okay, so the first thing you want to do is Arduino. You just select Arduino. So you really need Arduino IDE. So let's go to Arduino stores. So you need to install the Arduino IDE softwares. Okay, just the Arduino softwares is somewhere like softwares. Okay. Okay, so you need this Arduino IDEs. So this is a system that actually allow you to, including everything, so how to program it with a C++ language, and also the ways actually have some drivers to communicate. So you just click it and download it and install. I already do that, so this is fine. So when you actually plug in your Arduinos into the computer, okay, so there is something is going to show up. So if you go to the device managers, okay, so if you go to the device managers, you can see under the COM, so there is something is going to show up. So this one is USB series is COM4. Later on we're going to use this, so like you check which one is which. Okay, so the next thing you want to do is connect your Arduinos to Labview. So Labview need different softwares to actually doing it. So in that way, you need to do something like it's called a VI package manager, package managers. So it's this one. So VIPM. So here is it. It's just like click it and get it and download and install. So I'm not going to do it because I've already done it. So I already have the. So it's coming up. So like a VI package manager. So this is the newest version. Okay, I use a free editions, so there is nothing you need to pay. So you just make sure it's actually added in. Okay, it takes a while to actually load it, but when you actually load it, this software is going to able to help us to install all the add-ons as needed in the Labviews. Okay. Oops, sorry. So this is everything that I already installed on my computer. Okay, so this is already installed. But over here on the search bar, you just say Arduinos. Okay, Arduinos. Okay, so this is Arduinos. So there are several things actually. You can see. I just press this. Okay, so there is a Labview interface for Arduino. So this is made by the NI, our National Instrument. And there is a Digilant LINX, which is control the Arduinos, the Raspberry Pi, and ribbons and more. So this is more advanced versions of communicating with different kind of hardwares, particularly this open source hardwares. This time we're going to install this. So I'm going to click install. So this is says, okay, you're going to install this, you install this. I just click continue. Okay, I said I agree. Okay, then there's going to connect it to the Labviews, and they're going to try to open it. Okay, and they're going to try to adding the libraries to the Labview. Okay, so this is trying to add these things, and they're going to take a while. So be patient again. So this is going to be slow. Okay, so this does take some time. And it said, okay, there is a license packages. Okay, are you accept? Okay, obviously I have to accept. Okay, then you're going to install everything. Okay, so now it's everything is finished. So you can see this is says install. There is no errors. You just click finish. Once it finished, like before doing something here, we want to check a little bit things. So just go to your Labview over here. So this is a Labview Max. I'm sorry, NI Max. Give you some information about the communication port, whether they're actually connected correctly. So right now I'm already connected my Arduino Nano port to my computer USB. Okay, so once this is on, we're going to see how we can plug in everything. Okay, whether they actually can communicate correctly. Okay, so everything is opened. So like once it's opened, you want to check here. So like in the softwares. So you have the National Instrument Visa, so Visual Instrument Assistant. So like it's over here. So I have a very latest versions. And the next thing you want to go to the device and interface. And remember, we're talking about the Labviews. Right now, our Arduinos is currently using port 4. COM4. In COM4, you're actually going here and see this is a port descriptions, a USB series CH340s. Okay, sometimes it actually shows as Arduinos. If you're using Arduino Unos or you're using different kind of boards, they have different names, but make sure this is the one you're actually having. So over here, and you want to test it actually correctly. So there are some board rate settings, those kind of things. You don't need to worry too much at this moment, but like in later, if you're a more advanced one, so sometimes it could be matters, okay, for you. But in this case, I just don't. I want to test is it actually correctly functional. So I click here. Okay, so this is going into the instrument Visa testing panels. So over here, you can see all the settings, but you don't care about that. So you will go in here. So the input and output. You click right. Okay, you can see they actually correctly respond to my writing. So basically, that means actually I send a command there, and they're actually returning it. Like there is no errors. So that means the Arduino is correctly installed into the computer. So that's fine. So we can click close here. We can close this package as well. We can close this Max. Okay, and then like the first thing I want to do is click Tools and find there is something called Maker Hub and LINX, and called LINX Firmware Wizard. Click it, and they're actually coming in with a wizard. And then you want to select which one you want to connect it. So in this case, we want to connect it to Arduinos. So actually, you can see there's many things available. And there are Arduinos. In our case, we're actually using Nanos. So this one, click Next. So then we want to make sure it's actually going through the right port we're actually having. So this would take a while. Okay, so I actually try to search all the resources available on the computer. And now you can see, remember last time we said we're actually having the Arduino connected to the COM4. So in here, I click Next. Okay, so firmware versions is this, and previewed firmware. So just click Next. So they're going to upload the firmwares into the Arduino Nanos. So this is just communicating through the USB. Okay, so this one would take a little bit of time and configuring the devices settings. Once this is down, what I can do is make sure everything is fine. So I will launch examples just to make sure it's actually functional correctly. Okay, so in this case, they actually have a manual blinking example. So basically, there's going to have a little bit LEDs, or it's a little small LEDs on the device, and we want to make sure they actually could do is a blinking. So this is actually start to blink. So remember, this is a COM4, and LED is here. So when we actually hit start, okay, so it's actually here. So you can see over here I have a link, I have a LEDs on it. So when I click the source, okay, so they actually on and off like just by itself. So this just means I could use Labviews to correctly turn on and off a LED. So everything is working fine. Okay, so once we understand, like, connected the Arduinos to the Labviews, so next thing we want to program the interface program of a Labview controlling the multiplying DACs. Okay, so how this works, we want to understand the basics a little bit. Okay, how this multiplying DAC is really working. Because last time we were talking about we're using the AD7141 AKN to actually doing the job. Okay, so they actually connected with the AD7440. Okay, so if you go online, so you can search, okay, how this thing really works. Okay, in this case, like AD7541. Okay, so they actually have a data sheet is telling you how to wiring this IC together. Okay, you go online and search for this data sheet, and in here, essentially we're actually using this voltage diagrams over here. So you can see in the sheet we're actually using. So last time we were talking here. So this one, so I have a like 100 ohm, 33 ohms, and 33 picofarads. So if you look at here, so they actually have the same things. Okay, so we're using this 100 ohms and the 33 ohms. Okay, so this is the one actually using. So over here, we have a 12-bit information is coming in, and we want to see, okay, what kind of voltage output you actually could get. Okay, so this is a figure 4. This is a unipolar binary operation signals. So if you have input signals as Vin, what is output signals is. So if you have all things is on, so all the 12-bit information comes in is true, is coming in, you're actually getting the 4095, because the 1111 is 12.1 in the binary converted into the decimals is 4095. So 4095 divided by the 4096 multiplied by the negative of a Vin. So this is a number actually you're going to have in here. So like Vin is this. All right, so this is fine. Okay, this is a very simple one. Okay, but you can see this is actually called attenuation mode, or if you go to here, so like look at what the this is analog dialogues. Actually, AD is actually telling you what is the multiplying DAC is really doing. So in this way, it's called attenuation mode. All right. So the input signals is always going to be greater than the output signal. Okay. So that means, okay, so that means for us, so we have a 12-bit this information. So, okay, 12-bit multiplying DACs. We can have like 4096 stairs all the way to the input signal. Okay. Obviously, it's going to be reversed, but it's pretty much like that. All right. So with this, we can think about here. So if we have samples versus the potentiometers, and the potentiometer resistance has to be greater than the sample. All right. Otherwise, you're going to have the voltage here is going to be greater than this one, and the input is going to be even smaller. So there is no way you can match. Okay. So when you select the initial resistance of the potentiometers has to be greater than the samples at all time. Okay, all time has to be greater. Okay, and then we want to calculate. Okay, so we want to measure the sample first. Okay, and then we measure what is the potentiometer give it to me. Okay, or the A minus B. Okay, and then we can calculate the numbers by calculating numbers of the ratios has to be coming in from the multiplying DAC, and then after that by calculating I can cancel the A minus B. Okay, it becomes 0. Okay, so this is the flow chart we want to do. We want to measure this one. Okay, because we want to know what is the resistance of the sample, because this data is needed. The resistance of the sample Okay, because we know we first can measure the resistance of the potentiometers, okay, and compare what is the difference between here to here, and we know what is the resistance, the voltage in the A, and we know what is the voltage in B, and with VA over VB is going to give us what is the resistance of the sample, and then we try to balance this too by multiplying by some kind of numbers in here through the calculation of the whatever it is, and divided by the 4095. All right, and then we get this and input here and cancel everything. Okay, the frequency signal, so one frequency signal is going to be canceled from one A minus B, and then A minus B, and then we measure the triple frequency signal. Okay, 3 omega signal. All right, so I can create this flow chart for one frequencies. Okay. So we set the measurement at A. Okay, we measure A. Okay, at some frequencies, and then and the auto gains and reserve, and measure the X value, which is the resistance value, or the in phase values in the locking amplifiers, getting the VA, and then we do again and measure what is the V A minus B, because the system cannot measure B. So we will have to measure the A minus B. And once we get A minus B, we can, using the VA minus V minus B is equals to the VB. So we have the VA over VB multiplied by some kind of numbers. This is the resistance of the potentiometers is equals to the resistance of the sample. Okay, VA. And then we have the ratios, which is the VA over VB. Okay, multiplied by the 4095. So this is a whole ratio we want to put it into the multiply deck. All right. So with that, we set it in, and then we can remeasure the A minus B. The X ideally there should be 0. Okay, but we want to make sure it's very small. Ideally it should be 0, and then we convert it into the 3 omega signals. Take a measurement again, and then just continue. Okay, so I redo the flow chart. So it's basically like this. So this is measuring the 3 omega and auto gains, set the new frequencies, and basically scan the frequencies and get the 3 omega at all frequencies. So overall, everything has to be inside a loop of a different temperature. So you measure different temperatures, you're going to get it. Okay, so how to do that? So as I said, we're going to use the Arduino Nano to interface with a multiplying DAC DAC card. Okay, so essentially it's like this. So if you see over here, so I have a very simple program from the example. Okay, so if you go to the back, okay, so it's just something like this. Okay, so I open a series port, and in the series port, and it's like this is a source coming in, and I have a series port, and in here I have a loop, and in the loop this is a digital write, but it's N channel, because usually like in the example provided, they're actually using the 1 channel, because here we have a 12-bit of channels to actually doing it. So we need 12. Okay, so then they have several things. So you click the help, you can see you click help over here, so you see what it is. So here the first one is actually having the DO channels, so how many channels and what is the value. Basically is a series of true or false, and put it in, and then it's going to update the on and off for the system. Okay, for the Arduino port, basically from the DO. So here I actually change it a little bit, so I basically I show you one more time. Okay, how to do that. Okay, it's actually very simple. So you go here, click on right click, and then it says create a constant. Actually, you can create a control. So when you create control, you can actually see here on the front panels there is a bunch of things. Okay, there are a bunch of things. So down here we can select the first channel is 2, the basically DO2, D2, and this is a D3. So in this way, so this is the what is the channels over here. So all the channels, all the channels, so it would be easier. So all the channels is coming in, and the information I want to get it, because remember in the flow chart, okay, in the flow chart, it's actually the numbers, okay, some kind of numbers, and have a ratio, and this ratio multiply the number of 4095, and then I want to convert this number into a binary number. Okay, this binary number is basically my booleans. Okay, it's basically a series of true or false. Okay, and I have oh sorry, yeah, on the front I have it. So numerical control, I have some kind of numbers. Okay, so this numbers, okay, needs to be converted, okay, into some kind of multiply by a number. Okay, multiply by a number, and this number is create a constant. Okay, 4095, and I would round it up. Okay, round it to nearest value, and then this nearest values is basically integers. I could write it up like coming it out. So like show it, create a indicator. Okay, and then next thing I want to convert this integers into booleans. Okay, into a booleans. So this way it's easier ways to do is programming. Okay, booleans and number to array of booleans. Okay, so basically this numbers is going to be converted into 0 and 1, so a series of 0 and 1. But this one, it needs to be a little bit careful because this number cannot be over 2095. Okay, otherwise it's going to be a problem. It's going to be flow out. All right, so when you have a programming, but we can do that. Okay, we can actually do it. The limit. Okay, so the limit, the smallest number is 0. So the largest one is going to be like basically 4095. Okay, it's not going to be more than I'm sorry, no, the maximum number is going to be 1. Okay, so it's because I have a ratio, as this ratio is coming in, and this ratio is between 0 and 1. So as I said, like it's always going down. So like the number fit into the DAC card is going to be always attenuated a little bit. Okay, so attenuated a little bit. Okay, and if let's go outside, okay, I say coherence. Okay, coherence. Coherence means that if I put a number, let's say 5, okay, it's become 1. Okay, it's basically, if it says, okay, this number is -4, it becomes 0. So something like that. So the only number I can put in correctly is going to be 0.5. Okay, it's between 0 and 1. And then this one become a series of Boolean array, and this Boolean array is fitted into the value of updating in the digital write, and this is all I need to do to control a series of booleans over here. So like if I run, I would get a series of this on coming from here, depending on what value I actually set. Okay, so based on this, so we can start programming. So like this is saved for the next videos.